A black paper envelope lies flat on the laboratory bench in Paris. Beneath it, a photographic plate waits sealed in complete darkness. On top of the paper, a small quantity of uranyl potassium sulfate rests. No lamp has been lit. No sunlight reaches the surface of the salt. The year is 1896. Wilhelm Röntgen has just transformed the practice of physics. His X-rays pass through flesh and register their passage on photographic film. Henri Poincaré proposes that fluorescent bodies might emit invisible radiation. Bodies activated by prior exposure to light become the first obvious suspects. Henry reports photographic images produced by zinc sulfide through black paper. Niewiengowski repeats the test using calcium sulfide. Troost reports similar results. None of these results survive attempts at repetition by other investigators. The evidence dissolves under further examination. The question remains unsettled. Henri Becquerel approaches the problem with uranium. He knows the salt fluoresces. He places uranyl potassium sulfate on a wrapped plate and exposes it to daylight. Then clouds cover Paris for several consecutive days, and the experiment must pause. The prepared plates sit in a drawer with the salt resting on the paper in darkness. Becquerel develops the plates regardless, expecting little or no result on the emulsion. The impressions are dense and sharp. The salt has acted with undiminished intensity. No light has reached the uranium. No activation of the fluorescent property has occurred. The uranium has acted on the plate in total darkness without any external prompting. Becquerel then tests every uranium compound available to him in systematic order. Uranium sulfate, uranium nitrate, uranium oxide. Each compound behaves identically. Each one darkens the photographic plate through opaque paper placed between them. Each one passes its invisible emission through thin interposed screens of metallic foil. Each one discharges an electrified body held in proximity to the active surface. Metallic uranium proves the most active specimen of all those tested in the series. The emission belongs to the element uranium in every physical and chemical form it takes. Activity is measured electrically, not only by the action on photographic surfaces. Air enclosed between two flat metal condenser plates acquires the ability to conduct. When uranium powder covers the lower plate, a faint ionization current flows steadily. A piezoelectric quartz arrangement measures this current in absolute electrical units. A known suspended weight stretches the quartz crystal along a precisely defined axis. The crystal releases a calculable quantity of electricity per unit of measured time. This quantity is balanced against the ionization current produced by the uranium sample. The measurement is absolute and independent of the electrometer's own sensitivity. A saturation current is reached when the voltage across the condenser plate is large. This saturation value is the number assigned to the radiation's measured intensity. A single plate covered in powdered uranium metal is measured repeatedly for 5 years. The recorded saturation current values fall within 1 or 2% of each other. Temperature variation in the surrounding environment produces no detectable effect. The degree of illumination falling on the surface has no measurable influence either. The radiation persists unchanged in a compound kept for years in unbroken darkness. Gerhard Schmidt announces that thorium shares this same persistent atomic property. An independent measurement reaches the identical conclusion during the same period. Thorium and its compounds ionize air and darken plates without any external stimulus. They show no sign of consuming their own source. The emission does not diminish. A name becomes necessary. Substances emitting Becquerel rays are named radioactive. The word attaches to the observed property, not to any proposed internal mechanism. Uranium is radioactive. Thorium is radioactive. The property belongs to their atoms. Rutherford and other investigators examine carefully how the emitted rays travel. They search for regular reflection from smooth metallic surfaces. None is observed. They test for refraction as the beam crosses boundaries between different materials. The rays pass through matter without bending toward any interface normal. They attempt to polarize the beam using crystals and inclined metallic reflectors. No polarization is detected. In all 3 tests, the rays differ from Röntgen rays. Becquerel himself confirms after further work that his rays resist all 3 effects. The penetrating power of uranium and thorium rays falls well below that of X-rays. A few millimeters of solid material arrests the greater portion of the emitted beam. In open air, the radiation travels no more than several centimeters before it fades. This limited range suggests a closer resemblance to Leonard's secondary cathode rays. A pinch of salt on black paper. A sealed drawer. A measurement that does not waver. Matter emits radiation without being struck, heated, illuminated, or chemically altered. The emission belongs to uranium and to thorium as a fixed and inalienable atomic property. Radioactivity is not induced by any surrounding condition. It is not borrowed from light. Physics has needed a new word because the thing the word names was not previously known. A property always present inside matter has become visible for the first time to measurement, and the instrument that revealed it was a wrapped plate sitting untouched in a closed drawer. Glass jars line the shelf in labeled rows, each holding a substance. A measured layer of each substance covers the lower condenser plate. The electrometer is connected. The voltage across the plates is fixed. Every common metal in Ettores' collection at the École is tested first. Copper, iron, lead, silver, tin, and zinc are each placed in turn. The electrometer needle remains at rest through every one of those readings. Every non-metal follows in sequence. Sulfur, carbon, and silicon are measured. Not one of them produces a deflection sufficient to register on the instrument. Gallium is tested. Germanium is placed on the lower plate after it. Neodymium is measured, along with praseodymium in an adjacent run. Niobium follows, with scandium, gadolinium, and erbium after that. Samarium is placed between the plates. Ytterbium and rubidium follow. None of these substances deflects the electrometer needle by any amount. Moist white phosphorus is placed between the condenser plates. The air between the plates does acquire a conducting property, but phosphorus in these conditions undergoes a visible chemical change. It oxidizes and emits light while the measurement is being taken. Radioactivity is not altered by the chemical form that the element takes. Uranium sulfate, uranium nitrate, and uranium oxide all yield identical readings. The saturation current scales in exact proportion to the uranium content present. Every inert admixture functions only as an absorber of the radiation passing through it. The radioactive property belongs to the atom of uranium alone, not to any compound. Thorium behaves identically across every compound that contains it. Thicker layers of thorium oxide produce fluctuating readings that are harder to stabilize. Rutherford explains this irregularity by proposing that thorium emits an emanation. The emanation carries radioactivity within itself and is swept away by moving air. Both elements nonetheless share the same essential atomic origin of the property. The minerals are measured next on the same condenser plate apparatus. Pitchblende from the Johann Gorgenstadt deposit is spread on the lower plate. The electrometer deflects more sharply than it does for metallic uranium itself. The current is 4 times larger than the current produced by metallic uranium. Pitchblende from Joachimsthal registers the same anomalously high value. The ore sample from Pribram gives a comparable reading, as does ore from Cornwall. Cleveite, when measured, yields a current larger than its uranium content can explain. Chalcolite, a crystalline copper-uranium phosphate, registers twice uranium's activity. Autumite, a calcium-uranium phosphate, matches uranium on the condenser plates. Monazite, thorite, and orangite each register above what their uranium content predicts. Fergusonite produces the same kind of excess when placed between the plates. An unknown radioactive substance, present in trace quantities, would account for the excess. A controlled synthesis is prepared by Debray's method to test this hypothesis directly. A solution of uranyl nitrate is combined with copper phosphate in phosphoric acid. The mixture is heated to between 50 and 60 degrees Celsius. After an adequate interval, crystals of chalcolite form throughout the liquid. These crystals are grown entirely from individually non-radioactive starting materials. No unknown body has entered the preparation at any point in the procedure. The synthetic chalcolite is then measured on the same condenser plate apparatus. Its activity corresponds exactly to what its uranium content alone would predict. The synthetic mineral is 2.5 times less active than metallic uranium. The natural mineral, by contrast, is twice as active as the same metallic uranium. The gap between natural and synthetic chalcolite cannot be assigned to uranium. No known element can account for it. The natural mineral contains something else. That something is present in pitchblende, in chalcolite, in autumite. It concentrates wherever uranium concentrates, inside uranium-bearing ore. Chemical analysis cannot locate a substance it has no name to look for. Electrical measurement has no such limitation. It responds to activity directly. An active fraction separated from a less active one produces a measurable difference. The unknown body announces its presence through the deflection of the needle. 2 such bodies have now been identified through fractional separation of the ore. The first has been named polonium. The second, found with Bémol, has been named radium. Both bodies hide inside pitchblende residue in quantities chemistry cannot see. The instrument that revealed them was not a spectroscope or a chemical balance. It was a condenser, a quartz crystal, and a needle that would not stay still. Brown sacks of pitchblende residue arrive in loads from the Bohemian mines. They are stacked outside a wooden shed standing in the courtyard of the École. Large iron vats rest over open flames set directly into the shed's earthen floor. Its radioactivity measures 4.5 times that of metallic uranium. The Austrian government granted 1 ton of this material from Joachim Stoll. The intervention of Professor Suess secured the authorization for its transfer. What was discarded contains substances that no chemical method has yet identified. The residue is boiled with a concentrated solution of sodium carbonate. Radium, present as a sulfate, ranks among the least soluble substances in the mixture. Hot soda displaces the sulfuric acid. Silica and alumina pass away into the liquid. The remaining solid is treated with hydrochloric acid, free of any sulfuric acid content. Polonium precipitates from this solution when hydrogen sulfide is introduced into it. Actinium remains in the filtrate and is brought down separately by ammonia precipitation. Radium stays in the insoluble residue, resistant to hydrochloric acid throughout treatment. 1 ton of starting residue yields 10 to 20 kilograms of crude sulfates bearing radium. Their activity stands 10 to 15 times greater than that of metallic uranium. Polonium follows bismuth through 3 successive chemical separations from the residue. Vacuum sublimation of the sulfide mixture yields the first and most direct separation. The sulfide carrying the radioactive body is more volatile than pure bismuth sulfide alone. Precipitation of basic bismuth nitrate by adding water gives the second fractionation cut. From strongly acidic hydrochloric solution, hydrogen sulfide produces the third active fraction. A pure bismuth bar immersed in the active solution acquires a strongly active surface deposit. The liquid then contains only bismuth that is entirely without any radioactive property. Markwald, working independently, obtains a comparable deposit and names it radiotellurium. His material appears identical to polonium in both its origin and its chemical behavior. Once separated from pitchblende, polonium loses its activity at a measurable and steady rate. A sample of bismuth nitrate bearing polonium lost half its activity within 11 months. Radium shows no such complication. Its activity remains constant and reliably measurable. De Bierne identifies a third radioactive body within pitchblende and names it actinium. It accompanies elements of the iron group during the earliest stages of separation from the ore. Among the rare earths, actinium most closely resembles thorium in its chemical reactions. No complete separation of actinium from thorium has been achieved by any available method. The Académie des Sciences, the Société d'Encouragement, and an anonymous donor contribute funds. The Institut de France allocates 20,000 francs, enabling treatment of 5 more tons. Thousands of kilograms of starting material have yielded only a few decigrams of active product. De Marseille undertakes the spectroscopic examination of radium using spark spectrum photography. A new line appears in the ultraviolet region at a wavelength of 381.47 thousandths of a micron. It stands clearly apart from all known barium lines and registers at a significant intensity. As preparations of greater activity are examined, the line at 381.47 millimicrograms grows distinctly stronger. New lines appear alongside it. The barium lines decline in relative intensity across each plate. Further concentration yields a chloride in whose spectrum the new lines hold the dominant positions. De Marseille publishes a table of principal radium lines between 318.53 and 482.63 micrometers. 12 lines appear. The strongest receives an intensity value of 16 in the published table. 3 lines are designated strong, equaling the strongest known lines of any element examined. 2 nebulous bands appear alongside the sharp lines in the complete spectral record. The second begins sharply at 468.25, reaches maximum at 469.92, and fades gradually thereafter. The overall appearance of the radium spectrum resembles that of the alkaline earth metals. The first sample, showing the line at 381.47 micrometers, held radium at perhaps 1 part per million. Spectroscopic detection of radium requires activity 100,000 times that of uranium. The electrometer detects radioactivity at 1,000th of the activity of metallic uranium. Radiometric detection is therefore thousands of times more sensitive than the spectroscope alone. Polonium and actinium, examined by de Marce, yield only lines belonging to bismuth and to thorium. Of the 3 new bodies isolated from pitchblende, only radium has been obtained as a pure salt. Polonium remains embedded in bismuth. Actinium cannot yet be separated from thorium by any operation. A new element has announced itself through its own spectral lines, at its own wavelengths, in its own voice. The periodic table has received a body that makes itself known not by weight or color, but by light. A platinum crucible rests on the pan of an aperiodic balance. The balance was designed by Maria Curie for work of this precision. Its sensitivity extends to 1/100th of a milligram per reading. The substance inside the crucible is radium chloride in anhydrous form. Hygroscopic crystals draw moisture from the air, even within a drying case. Every weighing must finish before that absorption can disturb the mass. The chloride reached this crucible through fractional crystallization. The starting material was radioactive, barium chloride recovered from pitchblende. Radium chloride is less soluble than barium chloride in the same solution. This difference in solubility drives every separation in the procedure. The mixture is dissolved in distilled water and brought to saturation at boiling. Slow cooling causes crystals to settle on the floor of the evaporating dish. The liquid drawn off above the crystals proves 5 times less active than they are. 1 portion has become 2. The more active and the less active. Each portion then undergoes the identical operation in sequence. The least active fractions emerging at one end of the series are withdrawn. The most active fractions accumulate at the opposite end of the series. The number of working fractions is held constant throughout the procedure. In the early stages, 6 fractions were maintained in this way. When quantities become very small, plain water fails as a solvent medium. The volume remaining after crystallization grows too small to pour cleanly. Hydrochloric acid is then added to the water in a measured proportion. Chlorides are less soluble in acidified water than in distilled water alone. Crystals forming from an acidic solution appear as strongly elongated needles. Barium chloride needles and radium chloride needles are identical in appearance. The crystals of mixed barium-radium chloride emerge from solution colorless. When radium content crosses a threshold, coloration develops after some hours. The color passes from yellowish through orange. A pink tint appears in certain batches. This coloration dissolves entirely when the crystals are returned to solution. Pure radium chloride does not develop this coloring, or develops it far more slowly. Maximum coloration occurs at a specific intermediate concentration of radium in barium, when only the subsequent fractions color and the leading fraction does not. The end is near. At each stage, a few milligrams of the leading fraction are withdrawn for Demarce. He requires no more than this minimal quantity to photograph the spark spectrum. Chemical fractionation and spectroscopic verification advance together in this way. The first two atomic weight determinations used chlorides of lower activity. One had been enriched to 350 times the activity of uranium. The other had been enriched to 600 times the activity of uranium. Both returned values identical to those obtained from pure barium chloride alone. No difference from barium was yet detectable at those levels of concentration. A chloride enriched to roughly 1,000 times uranium's activity was used next. This determination produced a small but definite difference for the first time. The mean atomic weight from this sample returned the value 140. It was the first measurement to exceed the atomic weight of boron by a measurable amount. The method applied throughout was the classical precipitation of chlorine as silver chloride. A weighed mass of anhydrous chloride is dissolved and silver nitrate is added. The chlorine present precipitates completely as silver chloride from the solution. The silver chloride is collected, dried, and weighed on the same aperiodic balance. The formula assumed throughout the calculation was RaCl2, a divalent chloride. The atomic weights used for silver and chlorine were 107.8 and 35.4 respectively. A sample judged by Demarce to be probably pure was submitted to 4 determinations. That chloride still showed 3 principal barium lines at considerable intensity. The 4 values obtained for M were 223.3, 222.8, 224.0, and 223.6 across the series. Further purification reduced barium until only minimal traces remained in the spectrum. 3 final determinations were performed on this most nearly pure chloride. The weighed masses of anhydrous chloride was 0.0850, 0.1150, and 0.1021 grams. The silver chloride precipitates weighed 0.08915, 0.12015, and 0.10685 grams. The atomic weights computed from these three measurements were 225.3, 225.8, and 224.7. The three values yield a mean of M equals 225. The accuracy of the method was verified by applying it to pure barium chloride. Samples of 0.3 and 0.1 grams returned values falling between 136 and 137 for barium. The method therefore yields reliable results even when applied to very small masses. Radium's position in the periodic table follows directly from these measurements. It is a divalent element belonging to the group of alkaline earth metals. Within that group, it stands as the higher homologue of borium, above it in the series. Its atomic weight places it in the horizontal row that already holds uranium and thorium. Fresh radium salts resemble the corresponding barium salts in their chemical behavior. With time, all solid radium salts develop a progressively darkened color in the dry state. Every radium salt emits light in complete darkness, without any external illumination. Pure radium chloride is paramagnetic. Its specific magnetic constant K is 1.05 times 10 to the power of -6. Pure barium chloride is diamagnetic. Its constant K is measured at 0.40 times 10 to the power of -6. 50 kilograms of commercial barium chloride were subjected to the same fractionation. The least soluble fraction produced at the end of that series showed no radioactivity. The instrument detected nothing above background through the entire procedure. Radium does not appear in ordinary barium extracted from non-uranium mineral sources. It exists only in ores that carry uranium, concentrated wherever uranium concentrates. A platinum crucible, a dried anhydrous salt, a balance sensitive to 1/100th of a milligram. The number returned across 7 independent determinations settled at 225. That number assigns radium its place in the periodic table without ambiguity or appeal. The element that announced itself first through electrical deflection now carries a weight. The atom, once known only as an anomalous current on a condenser plate, has become matter. Its mass is measured, its valence is fixed, and its place among the elements is settled. A hollow has been drilled deep into a block of solid lead alloy. A grain of radium rests pressed at the very bottom of that hollow. A narrow pencil of emitted rays climbs upward through the open channel. The lead block sits inside a strong transverse magnetic field applied crosswise. A photographic plate waits horizontally above the open bore of the channel. The field acts on the rising pencil and bends its components apart. 3 separate groups emerge from what had appeared as a single beam. The gamma rays continue upward, with no detectable deviation at all. Their penetrating power is comparable to that of the Röntgen rays. No magnetic field strength yet applied has bent their path by any amount. The beta rays deflect strongly, curving away in a broad and continuous arc. On the plate, they form a wide band, a true continuous magnetic spectrum. Each individual ray within the bundle curves by a different radius of curvature. In open air, beta rays remain detectable at several meters from the radium source. The alpha rays bend only slightly in the direction opposite the beta deflection. Their radius of curvature is very large. The path departs barely from a straight line. A few centimeters of air arrests the greater portion of the alpha component entirely. The alpha rays from polonium describe curves identical to those of radium in the same field. The negative charge of beta rays was confirmed by a direct electrical measurement. A metal disc surrounded by an insulating layer was placed beside a radium-bearing salt. The disc connected by a wire to an electrometer, enclosed in a grounded metal box. Beta rays penetrated through the thin insulating barrier and through the thin metal wall. The electrometer registered a continuous accumulation of negative charge on the disc. In a reversed arrangement, the radium source itself connected to the measuring instrument. The radium charged positively as the beta rays carried negative charge outward into the disc. A small quantity of strongly active radium had been sealed inside a glass tube for some time. To open the tube, a glass knife was drawn across the wall to score a line across the surface. At the moment of scoring, an audible crack was heard distinctly from the tube. Under a magnifying lens, a puncture appeared precisely at the point the knife had marked. The tube had been pierced by the electrical potential accumulated through beta emission. Radium is the first body found to charge itself spontaneously without any external source. Becquerel measured both magnetic and electric deflection of the beta rays together. 2 quantities followed from the combined result: the ratio E/m and the velocity. His measurements returned approximately 10 to the 7th electromagnetic units for E/m. The velocity was found at 1.6 times 10 to the 10th centimeters each second. That figure lies close to the known speed of light propagating through empty space. Kaufman refined the measurement across beta rays of varying speeds and deflection angles. His results showed that E/m is not constant. It changes with the velocity of each particle. faster beta rays returned a smaller ratio. Rays of lower velocity returned a larger value. Thomson and Townsend had established that each beta particle carries one fixed unit of charge. If that charge is fixed and the ratio E over m falls with speed, then the mass m must be rising. The theory formed. The inertia of the particle grows as the particle accelerates through the field. Mass in mechanics may have its origin in the dynamics of small charged bodies moving at speed. The alpha rays had resisted deflection in earlier tests because the applied fields were too weak. Rutherford applied a sufficiently strong field and observed a small but definite curvature there. The direction of deflection was opposite to the beta rays, consistent with a positive charge. The velocity of alpha rays was estimated at 2.5 times 10 to the 9th centimeters per second. The ratio E over m for alpha rays equaled approximately 6 times 10 to the 3rd in those units. Radium emits all three ray groups, alpha, beta, and gamma, at the same time. Polonium emits alpha rays only. Uranium and thorium emit alpha and beta together. At large distances from any radium source, only beta and gamma rays remain detectable. The alpha component is exhausted within a few centimeters of open air and disappears. A beam once treated as a unified entity has resolved into three distinct material groups. Positive projectiles curve one way. Negative projectiles curve the other. Gamma rays travel straight. The beta particles move at velocities approaching that of light, and their mass is not fixed. The particle, whose trajectory seems simple, carries an inertia that grows with its own speed. The radiation leaving this small hollow in lead has exceeded the terms of its own measurement. A sealed glass tube rests inside an insulated Dewar isolator. It holds a few decigrams of radium bromide, sealed and still. The isolator is submerged in liquid hydrogen at -253 degrees. Gas rises from the liquid hydrogen in a steady, unbroken stream. 3 cubic centimeters collect above the cold surface each minute. No external heat source is present or applied. The radium is the cause. Curie and Laborde placed a sealed bromide tube inside a Dewar isolator. The interior registered 1.5 degrees above ambient temperature. Each gram of radium releases approximately 100 small calories per hour. 1 gram atom releases each hour an amount approaching the heat from combusting 1 gram atom of hydrogen. No ordinary chemical source can sustain this rate. Radium shows no visible alteration across several years of continuous emission. Dewar and Curie confirmed the result using liquid oxygen and liquid hydrogen. Continuous evaporation of hydrogen at -253 degrees, was measured and recorded. The radium inside the sealed tube produced that evaporation without ceasing. When the tube was wrapped in 2 millimeters of lead, total output rose noticeably. The penetrating rays carry energy outward through glass and escape unabsorbed. Lead arrests them. Their energy is added back to the measured total. A freshly prepared solid radium salt releases relatively little heat at first. Heat production rises over 2 months and then holds at a fixed limiting value. A dissolved salt in a sealed tube reaches the same limit in approximately 1 month. A radium preparation enclosed in celluloid or rubber was placed against bare skin. A red mark appeared at the exposed site after a delay inversely proportional to activity. Walkhoff observed the effect first. Giesel confirmed it independently. Becquerel and Curie after. Curie placed a preparation of moderate activity against his own forearm for 10 hours. Redness appeared almost immediately. A wound followed. It healed over 4 months. The skin was entirely destroyed and renewed only with exceptional difficulty. A visible scar remained after healing was judged to be complete. A 10-hour exposure to a weaker preparation produced a blister after 15 days. An exposure of 2 minutes produced a red mark appearing only after 2 months. Giesel placed a radium preparation beside a closed eyelid near the temple. A sensation of light was reported, filling the interior of the closed eye entirely. Himstedt and Nagel established that the eye's own substances phosphoresce under radium. Subjects blind from undamaged retinas reported the sensation. Those with damaged retinas did not. Danis exposed animals to radium rays for approximately 1 hour continuously. Paralysis followed. The animals died within several days of the exposure. Dr. Danlos at the Hôpital Saint-Louis applied radium to certain diseases of the skin. Skin destroyed by the application regrew in a healthy state. Results were encouraging. Glass and porcelain placed near a strongly active preparation become colored. The color, brown or violet, develops throughout the body of the material. It persists after the radium source is removed. Lead in the glass is not required. Giesel showed alkali, metal halide crystals, color under radium, as under cathode rays. White phosphorus converts to red phosphorus under radium's action. Paper in prolonged contact becomes brittle and perforated across its surface. Ozone forms wherever air reaches the surface of a radium preparation directly. A sealed tube produces no ozone. Contact with open air is required to generate it. Radium bromide solution continuously evolves gas from its sealed container. The mixture is predominantly hydrogen, and oxygen in proportions close to those of water. Solid chloride and bromide also evolve gas without interruption. The gas contains hydrogen, oxygen, carbon dioxide, and helium. Ramsay's spectrum of this gas showed several additional lines of unknown origin. A sealed tube accumulates internal pressure. Slight warmth is sufficient to cause rupture. At liquid air temperature, radium continued to glow without diminishment. Electrical measurement showed the same intensity at -190 degrees as at room temperature. Prolonged heating reduced activity by as much as 30% of the full total. The penetrating rays were almost entirely suppressed during heat application. Activity recovered fully within 2 months after the elevated temperature was removed. Every body placed in the vicinity of a radium salt becomes itself radioactive. Pierre and Marie observed this, named it induced radioactivity, and determined its laws. The induced property does not arise from dust deposited on the receiving surface. The activity of an exposed plate rises asymptotically toward a fixed limiting value. After removal from the source, it falls asymptotically back towards zero. The nature of the receiving substance does not alter the result. Lead, copper, glass, paper. The same limiting value is reached for every substance exposed to the same preparation. Negatively charged bodies, Rutherford found, activate more strongly than neutral ones. In a closed vessel, induction proceeds regularly to a fixed limit every time. Gas drawn from the sealed space carries its radioactive property into a second vessel. This gas, the emanation, activates the walls of whichever container receives it. Radium, thorium, and actinium each produce their own distinct emanation. A solid body activated by radium in a closed space, then removed, loses its activity. After several hours, decay follows a fixed law, halving every 28 minutes. The walls of a sealed vessel retain activity longer, halving every 28 days. Temperature between -38 and 210 degrees has no effect. Radioactivity has crossed the boundary of the body that produced it. It has passed through the surrounding gas and settled into indifferent matter. Lead, copper, glass, and paper possessed no radioactive property before the exposure began. After exposure, each one emits rays. The electrometer measures them without ambiguity. The property once attributed to a specific atom in a specific mass has become mobile. What the radium salt possesses, the space around it begins to acquire in measurable degree. Radioactivity in the vicinity of radium is no longer the fixed attribute of one substance. It is a condition that extends outward from the source into every material within reach. A sealed glass ampoule rests on the stage of de Marchay's spectrograph. Inside it, a few milligrams of radium chloride sit undisturbed. 12 months have passed since the ampoule was placed there and closed. The spectrum has been photographed at intervals across the entire year. Not one line has shifted. Not one new line has appeared in the record. The radium has not become borium. It has not become any other substance. Becquerel had earlier precipitated barium sulfate from a uranium solution. The sulfate carried away a fraction of the uranium's measured activity. The uranium left behind showed a weaker current on the electrometer plates. This seemed at first like a permanent division of the radioactive property, but within a few months, the uranium recovered its original full activity. The barium sulfate, meanwhile, lost the activity it had taken from the solution. No permanent subtraction had occurred. The activity had only been borrowed. Rutherford performed the analogous separation using thorium in solution. Ammonia precipitation drew off a weakly active thorium hydroxide from the liquid. The residue left behind evaporated to dryness, proved intensely radioactive. Rutherford named this concentrated active fraction thorium X. Thorium X then faded steadily, while the depleted hydroxide recovered its strength. The total radioactivity of the system did not decrease across the exchange. It redistributed, reached its limits, and returned each portion to its prior state. Activity behaved as a quantity that flows, accumulates, and is continuously renewed. Curie and Debian constructed a general theory to account for these observations. The theory requires no hypothesis about the internal cause of radioactivity itself. Each atom of radium is treated as a constant and unchanging source of energy. That energy disperses through two distinct channels operating simultaneously. The first channel is radiation, charged and uncharged rays emitted outward. The second channel is conduction, emanation carried into surrounding gases and liquids. The emanation transforms in those surrounding bodies into induced radioactivity. Loss through both channels grows as the stored energy inside the body increases. Equilibrium arrives when the rate of loss exactly equals the rate of production. This formal structure resembles the equilibrium of a self-heated thermal body. Heat produced internally raises temperature until radiation and conduction match output. Radioactive energy produced internally raises the stored level until loss matches supply. The theory explains several observations that had previously resisted connection. A freshly prepared solid radium salt begins with relatively low measured activity. Over approximately 1 month, that activity rises toward a fixed limiting value. The emanation cannot escape easily through the solid crystalline body of the salt. It accumulates inside the grain and converts there into becquerel rays. A dissolved salt in an open vessel behaves in the opposite manner at first. It begins strongly active, then loses activity as emanation escapes into the air. Sealed inside a closed container, the dissolved salt accumulates its emanation again. After roughly 15 days, the sealed solution returns to a high limiting value. A solution exposed to open air does not recover its activity when sealed afterward. This last result separates two effects: loss through radiation and loss through conduction. Heating a radium-bearing salt drives emanation outward faster than it would escape normally. Induced radioactivity in the surroundings intensifies during the period of heating. After the salt cools, it behaves as if freshly dissolved, with low initial activity. It then slowly climbs again toward its limiting value over the following weeks. Strong, prolonged ignition to red heat destroys nearly all penetrating ray production. After such treatment, however, the limiting value the salt eventually reaches is higher. The physical change induced by heat impedes the future escape of emanation from the grain. A greater internal accumulation results, and the salt radiates more intensely thereafter. Radium, thorium, and actinium each produce their own distinct and separate emanation. The emanation of radium decays to half its initial activity every several days. Thorium's emanation reaches the same halved value in roughly 1 minute and 8 seconds. Actinium's emanation is faster still, halved within a few seconds of its production. Atmospheric air, Elster and Geitel found, carries a small quantity of radioactive emanation. This atmospheric emanation appears identical in character to that produced by radium. Waters from certain mineral springs release emanation into the gas above them. Water from rivers and seas carries no detectable emanation under examination. The emanation itself behaves in many respects like a material gas under ordinary conditions. Connected vessels share it by diffusion, as any gas follows the laws of pressure and volume. Rutherford and Soddy showed it condenses in liquid air alongside other condensable gases. Its diffusion coefficient in air does not differ greatly from that of carbon dioxide. Yet the emanation also vanishes spontaneously inside a sealed glass vessel with time. No detectable pressure from accumulated emanation has been established by measurement. It penetrates through gaps that ordinary gases cross only with the greatest difficulty. Its condensation temperature does not depend on concentration inside a given volume. Rutherford and Soddy compare the emanations for these reasons to the argon group. They resist energetic chemical reagents and share the chemical inertness of noble gases. Ramsey and Soddy found that the gases released by radium contain helium, that helium forms gradually in the presence of radium emanation during its decay. The emanation appears to be an unstable gas that decomposes into helium as a product. The question of origin cannot be deferred once the facts reach this arrangement. Where does the energy come from? Each hypothesis has been examined against the record. One proposal holds that radioactive energy was stored long before observation began. The atom releases it slowly, as a phosphorescent body releases captured prior light. This proposal has the disadvantage that the energy shows no detectable diminishment. De Marcy's 12-month spectroscopic vigil over pure radium chloride confirms this. A second proposal holds that atomic transformation accompanies the energy release. Radium emits heat continuously. That rate cannot be sustained by any chemical reaction. A transformation losing material particles with each emission would supply such a rate. A third hypothesis places the source of energy in gravitation acting on the atom. A fourth imagines unknown cosmic radiations absorbed and re-emitted as Becquerel rays. Elster and Geitel measured uranium's activity at 300 meters below the surface. A layer of Earth that thick produced no detectable change in the measured emission. If a solar radiation were responsible for uranium's radioactivity, the Earth itself would have screened part of that radiation when it lay between uranium and the Sun. Measurements taken at noon and at midnight showed no difference from each other. Villard exposed a piece of bismuth to cathode rays inside a Crookes tube. After 40 days of exposure, the bismuth produced faint impressions on photographic plates. McLennan exposed various salts to cathode rays and then warmed them slightly. Those salts then discharged a charged electroscope in the manner of radioactive bodies. These results suggest that known physical agents may one day produce radioactive matter. If inactive substances can be made radioactive, the origin of the property becomes tractable. The new radioactive substances appear exclusively in minerals that also contain uranium. Radium has not been found in any barium compound extracted from non-uranium sources. The same uranium-bearing minerals also contain argon and helium in their structure. Ramsey and Soddy's result now connects the helium to the emanation's decomposition. The simultaneous presence of uranium, radium, argon, and helium in the same minerals implies that the existence of each may be connected to the formation of the others. Some elements may arise from other elements under conditions still not understood. One further alternative remains open alongside atomic transformation as a hypothesis. The radium atom may not itself be transforming. It may remain stable and unchanged. Instead, it may act upon surrounding matter, inducing atomic changes in other bodies. This version also requires that atomic transmutation is possible in principle. But in this case, radium would not be a diminishing element. It would be a catalyst. The evidence does not yet resolve which hypothesis corresponds to what actually occurs. A sealed ampule on a spectrograph stage, 12 months. An unchanged spectrum. The property flows, accumulates, and returns. Never permanently lost, never exhausted. The theory accounts for what is seen. The cause of what is seen remains unresolved. Radium sits in uranium minerals alongside helium and argon in chemical kinship. Emanation decays into helium. Helium accumulates inside rock alongside uranium and radium. These coincidences have the shape of consequence, one thing arising from another. The atom that emits continuously and transforms nothing detectable in a year of watching may nonetheless be altering, particle by particle, imperceptibly, across vast time. The inquiry that opened with a wrapped plate and a pinch of salt has arrived here, at the question of whether matter, at its foundation, is permanent or in motion. Physics does not yet possess the instruments to answer. The question is left standing. The script was based on the book Badanie, ciał, radioaktywnych, authored by Maria Skłodowska-Curie and first published in 1904. Thank you for watching. Until the next journey begins.